Hello everyone, my name is Wyatt Locklear, and for my Math and Nature project I chose the honeycomb conjecture. Now, many insects such as wasps and bees use honeycombs for storing and living space. But why is that? It is because, mathematically speaking, the honeycomb is the most efficient way of storing things. Now, let me explain. The honeycomb conjecture theorem 1a states that for the perimeter is T multiplied by the intersection of B 0, R, which is greater than the line sub of R. Let me make that make sense and explain some of these variables. T stands for tiling. So the perimeter is the tiling multiplied by the intersection of B 0, R. That stands for disk radius. So the tiling multiplied by the disk radius is greater than the line sub of R, line sub being limit superior, which is the largest accumulation point. That is perimeter, the equation to find the perimeter. For the area is C with the intersection sign multiplied by B 0, R, all over, as in that's a numerator, and the denominator is R. So this we have a new variable introduced, which is C. C is the competing tiling, which can be different shapes or structures. Now, the numerator for the area is the portion of the competing competitor tiling that falls within the disk of the radius. Now, this expression appears to compare perimeters at different tilings about their areas. So this doesn't make a lot of sense. So let me sum this up. The honeycomb is the most efficient way because when comparing all possible ways to partition a surface into regions, the proof, the equation, shows that hexagons, which are the shapes inside of a honeycomb, require the least amount of boundary length. Meaning that when you have a honeycomb, there's each individual cell, which is a hexagon. Those individual cells are, for how small they are and their size, are the most efficient way to store things. Their honey, food, living space, whatever, is the most efficient way. Because Thomas Hale found this equation, he did the math using this equation that I just told you, theorem 1a, and found out that hexagons are the most efficient way comparable to other shapes such as squares, circles, rectangles. The hexagon in the honeycomb is the most efficient way. Thank you.
Hi guys, my name is Michaela, and for my Math and Nature project, I chose the topic of probability, and I'm going to tie that to fission for the example. Probability, the formulas we're going to use for it is going to be P parentheses of E, which equals the number of favorable outcomes divided by the total number of possible outcomes. So when you're fishing, there's a lot of factors you can tie into it. It's location, time of day, weather conditions, bait and tackle. There's many other factors also, but I chose to only list these. Location. There's different bodies of water can have different populations of fish. The time of day. Fish are more active at certain times, such as early in the morning or even late at night. Weather conditions. Weather also affects fish behavior, with certain fish being active in specific conditions, like more fish could be active during the rain because that's just how their nature works. Bait and tackle. The choice of bait and fishing gear can also encourage the chances of attracting a fish. Like, say you have a worm that's really big, then you are more likely to catch a bigger fish because the fish is obviously going to go for more food because it requires more food because it's a bigger fish. So for my example, I'm going to be using a made-up fisherman named Mason. And it says, imagine a fisherman named Mason. He is fishing in a lake that is known to have 200 fish. On any random day, the probability of a fish biting is influenced by the factors that were mentioned earlier. So like location, weather, bait, and tackle. Imagine Mason has determined through observation and experience that the probability of a fish biting is 0.05 or 5% during the fishing times. If Mason makes multiple attempts, the probability of not catching a fish in all attempts can be calculated using the formula P parentheses EN parentheses equals P parentheses EN. And we're going to let N be the number of attempts that Mason makes. So let's imagine Mason makes 10 attempts, so we'll put the 10 in the place of the n and we'll multiply it. And P parentheses E times 10 equals 0.95, 10, and then we add 10 at the end also for the n, and it will be approximately 0.5987. So the probability of not catching a fish in all 10 attempts is approximately 59.87%. To find the probability of catching at least one fish, we can subtract this value from 1. So we'll subtract 1 from the 59.87. And so down here below it says P catching at least one fish equals 1 subtract P E10, and P catching at least one fish equals 1 subtract the 0.5987 equals 0.4013. Therefore, the probability of Mason catching at least one fish in 10 attempts is approximately 40.13%. This is all for my presentation. Goodbye.
Have you ever noticed patterns in nature that seem almost too perfect? From the spirals of sunflowers to the structure of galaxies, many natural designs follow a special mathematical ratio, 1.618, known as the golden ratio. The golden ratio, represented by the Greek letter phi, is approximately 1.618. It appears in the Fibonacci sequence, which each number is the sum of the two before it. As the sequence grows, the ratio between consecutive numbers gets closer to 1.618. Let's see how the golden ratio appears in a real-life example. A nautilus shell. The shell spiral grows outward following the golden ratio. Suppose the radius of a smaller spiral section is 3 centimeters. To find the radius of the next larger section, we multiply by the golden ratio 1.618. This means the next section of the spiral will have a radius of 4.85 centimeters. As the shell continues to grow, each new section expands by the same ratio, keeping the spiral perfectly proportional. This is why the nautilus shell maintains its beauty and balanced shape. We see this ratio everywhere in nature. Sunflower seeds grow in spirals that follow the Fibonacci numbers, allowing them to fit perfectly. The nautilus shell grows in a golden spiral, expanding in proportion as it gets larger. Even the human face follows the golden ratio. Beyond Earth, even galaxies form spirals that match this ratio. But why does nature follow this pattern? The golden ratio helps maximize efficiency, balance, and beauty. Plants use it to grow in the most space-saving way. Animals and humans develop with proportions that promote stability and movement. Even in the universe, it shapes the very fabric of existence. The golden ratio isn't just a number. It's a blueprint for beauty and function in the natural world. Whether in plants, animals, or galaxies, this mathematical phenomenon connects everything around us. Next time you look at nature, you might just see math in action.
For my math and nature problem, I'm going to solve for the height of a tree, which for now I'm going to label x equals question mark, because that's what we're solving for, by using the angle of elevation to the sun, which is 38 degrees, and the length of the shadow, which is 213 feet. Now to find this, I'm going to use the trig function tan, which is opposite over adjacent. This is the adjacent side to the angle, so we're going to label this A, and then this is the opposite side of the angle, so we're going to label this O. So to find the height, we're going to put all this information into this formula. So it's going to be tan of 38 degrees is equal to, it's opposite over adjacent, but I'm going to put x instead of O over 213 feet. Now to find for the height, we're going to multiply by both sides, multiply 213 by both sides, and that cancels out. And then we just bring all of this down. So it's going to be 213 times tan of 38 degrees. And so once we put this in our calculator, make sure that your calculator is in degree mode, Our opposite length, or our height, would be 166.4 feet.
Friction, a process that happens 24/7. We all know it. We've all heard of Newton and his laws. We all know how friction works, but what you might not know is that math can represent it. Why? Well, can't cover it in this video, but here's what you have to know. Dry friction is represented with this formula. Ff meaning frictional force, Fn meaning normal force, and this weird Greek letter meaning coefficient of friction. This equation shows us how to find frictional force, but how can we find normal force and coefficient of friction? Normal force is basically how an object reacts to the surface it's on, measured in newtons. Without normal force, an object can fall straight through a surface. We'll use mass, gravity, and incline to find it. Coefficient of friction is a number representing resistance to motion. It sounds similar to frictional force, however, this is dimensionless, meaning you can't measure it with a unit like newtons. This chart shows typical coefficients for different materials. We'll use this later. 30-gram wood box is sitting still on a wood ramp. The incline is represented by a point on the unit circle. Assuming the box is present on Earth, state the amount of frictional force that keeps it in place in newtons. First, let's find frictional force. Calling back to the formula, we'll put in these values. First is mass, second is approximate Earth gravity, and third is the cosine of the incline. It'll come out to about 259.8 newtons of normal force. Next, we use the coefficient of friction chart again, knowing that both materials are wood. We can see that our coefficient of friction is 0.25. Finally, we'll use the initial equation with our new values. That'll get us a frictional force around 64.95 newtons.
For my project, I was comparing someone's weight on the moon to their weight on the Earth. And I did an interview with my science teacher at the high school I go to, and he told me that the reason people's weight would be different is because of the size of the place they're on, the mass it takes up, gives it a different gravitational pull. Since the moon is much smaller than the Earth, it has a much smaller gravitational pull than the Earth does. Therefore, someone's weight on the Earth is much larger than their weight would be on the moon. The formula I got for converting someone's weight from the Earth to the moon is moon weight equals Earth weight divided by 9.1 times 1.622. So I used my own body weight on the Earth, 197.8 pounds, divided it by 9.81, and then multiplied that by 1.622, and I got that my moon weight is approximately 32.7 pounds. That's a much smaller weight than the Earth, and that's, like I said, because of the gravitational pull. So that just shows how much the gravity really determines someone's weight.
Hello everybody, my name is Eric Zing, and this is my math and nature project, Packing Planets. So the question I want to answer is how many Earths can fit into Neptune? And to do this, we need to make just a few assumptions. The first one is that both planets are perfect spheres, and the second one is that the Earth can pack into Neptune with no space left over. I made these two assumptions for simplicity, because we know that planets are not perfect spheres, and that Earth, when packing into Neptune, will likely leave some space. But making these two assumptions makes the math a little easier. So the information I need to answer how many Earths can pack into Neptune is the diameter of Earth in Neptune. Earth has a diameter of 12,750 kilometers, and Neptune has a diameter of 49,528 kilometers. And next, I need to find the radiuses. Earth has a radius of 6,375 kilometers, and Neptune has a radius of 24,764 kilometers. And I just divided their diameters in half to get their radius. Next, I need to plug both values into the volume formula. So, plugging in the radius of Earth, I get this. And plugging in the radius of Neptune, I get this. And the next step is to simplify by multiplying in d4/3. And this is the volume of Earth and Neptune. And the last step is simply to divide the radius of Neptune by the radius of Earth. And in the end, 58.62 Earths can fit into Neptune.
The beach. A unique place where the grand green land meets the vast blue ocean. Standing only a few feet away from a whole different world, it seems daunting to know that humans found a way across this seemingly never-ending void of water. Looking ahead, there's no sign of land, just the view of the water and the free sky. You may remember learning when you were young that there are 7 continents spread across the earth, but you can't see one in the distance. Why is that? Well, that's because the earth is a sphere, not flat, and thus you can't see past the horizon line. For those who do not know, the horizon is the visible line where the sky meets the ocean. At this line, you visually see the point of collision between the sky and the water, but in reality, you actually see the ocean bending out of your view. If this seems confusing, don't worry, you're not alone. This is the Earth, the home of all living creatures. Here, you can see the United States. If we were standing on the east coast of the United States and looking towards the Atlantic Ocean, you would not be able to see Africa on the other side. At the horizon, your view gets cut off. However, where exactly is the horizon at? To figure that out, let's further simplify what we're looking at. By turning the Earth to where the US is at the top of the circle and Africa is to the right, we can think of it as a circle. With this circle, we're assuming the Earth is a perfect circle. It's not, but it's easier to work with and will be accurate enough. Next, we break it down into various parts. The parts that we will use are the radius of the Earth, written as r, the height from where we are observing from, written as h, and the distance from our eyes to the horizon, written as d. To begin, we start by drawing the radius of the circle since it's the easiest to draw. Next, we can write the height from where we will be viewing the horizon. And lastly, the distance from our eyes to the horizon. From what we can see, the radius and the height are combined into one line, and the distance from our eyes to the horizon appears to be a tangent line because it intersects with only one point in the circle. That means the tangent line forms a 90-degree angle, and so we can form a right triangle. This is good for us because whenever we plug in values for the variables we know, which are r and h, we will be able to find the missing side d using the Pythagorean theorem. Now, using data from NASA to find the radius of the Earth and measuring your own height up to your eyes, we can use 6,378 kilometers, or about 3,963.1 miles for the radius. And then, we can use 6 feet as a base plate for the height of the person. Since miles and feet are not the same unit, we have to convert the miles down to feet, giving us about this many number of feet. Now that we have to solve for d, we just set it up like this. Or, when finalized, it looks like this, where d equals the square root of 2 times this massive number times 6 plus 6 squared. Using Desmos to calculate this, we get the answer, 15,846.2 feet, or about 3 miles. Isn't that pretty neat how we could find a distance to something that, technically, we can never get to even if we tried? Also, this formula will work for any planet's horizon, as long as you use the correct values. But whatever. My name is Christopher Martin, and this is how you find the distance to the horizon.
Math and Nature Project. Did you know that the wings of butterflies are a beautiful example of how math shapes the natural world? This video will cover types of symmetry, mathematical analysis, and significance. And my problem is, a butterfly exhibits bilateral symmetry, with its wings as mirror images across its body. Each wing measures 12 centimeters from the body to the wingtip. The angle between each wing's upper and lower edge of each wing is 45 degrees. If we consider the butterfly's wing as part of a figure, calculate total wingspan, area of each wing, the height, and the angle of rotation. For total wingspan, with each measure 12 centimeters from body to tip, the total wingspan is 2 times 12 centimeters, which equals 24. Area of each wing, assuming each wing approximates a triangle, its area is calculated using the formula area equals base times height times 12. Using trigonometry, the height from the 45-degree angle is height equals 12 centimeters times sine of 45 degrees, which equals 12 centimeters times 0.7071, which equals 8.49 centimeters. Therefore, the area is 12 times 12 centimeters times 8.49 centimeter, which equals 50.94 centimeters squared. For angle of rotation, to map the left wing onto the right using rotation, 180-degree rotation around the body aligns the two sides, demonstrating rational symmetry. In conclusion, butterfly symmetry has both biological and mathematical importance, as aerodynamic design improves flight efficiency, while symmetrical patterns aid in hiding from predators or attracting mates. By mathematically quantifying dimensions and angles, we gain deeper insight into those natural sensations, bridging the gap between geometry and biology. Thank you for listening.
Hello, my name is Zoe Viggies, and this is my Math and Nature project. I did my topic on bacterial growth. Bacteria is an organism that is found everywhere. The organism is found in all different types of forms and are very crucial aspects of the environment on Earth. Bacterial replication is when bacteria reproduce and increase their population. Bacteria are prokaryotic organisms, meaning they are single-celled organisms. Due to the lack of complex organisms, they cannot undergo mitosis or meiosis, a process that eukaryotic cells use to duplicate. Instead, they replicate and divide through binary fission. Here's our given question. In microbiology class, you cultured a population of Salmonella. You are asked to start with an initial population of 100 bacteria, and the growth rate is known to be 0.3 per hour. We are asked to find how many bacteria will be present after 5 hours of growth. We can use the exponential growth rate formula to find the answer. Here's the exponential growth model and the formula that we'll be using to find this answer. So first you want to plug in everything that was given to us into the formula. Then you want to calculate 0.3 times 5, and that equals 1.5. Then you want to use your calculator to find e to the power of 1.5. After you do that, your answer should be approximately 4.4817. Lastly, you plug in what you have into your equation, and you should have approximately 448.17 as your answer. Now, you want to round down so you can get a solid number. So after 5 hours, the bacterial population will be approximately 448 bacteria. Thank you.
Nature. Everyone, yes, everyone loves nature. Except for this thing. This is a mockingbird. Let me explain. I'm doing my math homework, but a bird kept chirping nonstop outside my window. So I did what anybody would do. Close the window. But it was still so loud that I could not focus at all. And that made me come up with an idea for this project. But first,
I just want to talk to him. Why do you have a shotgun?
I just want to talk to him.
Welcome to Connor's amazing math lesson. And for this project, it's going to be on sound. This is a longitudinal wave. It moves parallel to the equilibrium and is how sound travels through air. It uses compressions and rarefactions. This can be converted into a transversal wave, which the compressions become the peaks and rarefactions are the troughs. It's essentially a sine or cosine function. Step 1. Use the function a times sine of 2 pi times f times t plus phi, where a is the amplitude and determines the volume, f is the frequency of wavelengths in a period, t is the amount of time, and the symbol phi is the phase shift. The period is 1 because 2 pi divided by b is essentially 2 pi divided by 2 pi, which is 1. And the 1 is measured in seconds. Now for the amplitude. For this project, A is measured in micropascals. The formula to convert decibel sound pressure levels is A is equal to 20 times 10 to the power of decibels divided by 20. The function works like any other sine function, with the A vertically stretching or compressing, F horizontally stretching or compressing, and phi moving the function left and right. You can think of the t as the x variable. Now to do this in nature. All I have to do now is just find a natural sound wave. What is that? Is that a sound wave at 20 hertz of frequency? At 60 decibels? Wait, then what's...
Hi, I'm Chef Jacoby, and welcome to the bakery.
Now since it's 60 decibels, A is equal to 20 times 10 to the power 60 divided by 20, which is A is equal to 20 times 10 to the power 3. 10 to the power 3 is 1000, so 20 times 1000 is 20,000, which makes A 20,000 micropascals. Now since the frequency is 20 hertz, we can just plug that all in, making the function. Since there is no phase shift, there doesn't have to be a variable for that, making the function 20,000 sine of 2 pi times 20t. Hooray! And we can also graph the mockingbird chirping outside my window by breaking the complex sound waves into simple sound waves using the Fourier series. This sound has thousands of frequencies, but I chose 10 of the most dominant ones and put them together. And this sound is vaguely similar, just really not that close. Just have a listen. Hooray, that's the end. Bye-bye.